At the end of this year, I got completely hooked on a game I've wanted to play for ages, Kerbal Space Program. For those who have played it, you are probably aware of the relative difficulty involved in building a stable spacecraft and managing the entire launch process. But what surprised and amazed me most about this game is the incredible attention to physics details the developers put into it. It turns out, the game follows the exact same principles as real life, just in a slightly more simplified way. In the vehicle assembly building, you will find many different structures that can be connected together, like motors, fuel tanks, and aerodynamic pieces. However, to build a stable rocket, we must consider that mass is a dynamic variable that governs everything from orbital reach to aerodynamic stability. Unlike a car, which maintains roughly the same mass throughout its journey, a rocket is what we call a variable mass system. Because of this, we have to constantly manage the relationship between the wet mass, the fully fueled vehicle, and the dry mass, which is the vehicle after the fuel is gone. Every launch from the Kerbal Space Center is a practical application of the conservation of momentum, orbital dynamics, and energy management. On the launch pad, our rocket is stationary, fighting the downward pull of Kerbin's gravity. To rise, we must generate an upward force greater than our weight. When we ignite the engine, we start to throw exhaust gas downwards at high speed. Since the rocket is ejecting mass, we look at the change in momentum of that exhaust. This allows us to define the thrust force. Essentially, the thrust is determined by the rate at which mass leaves the engine multiplied by the velocity of that exhaust. There is also a pressure factor to consider. For the real thrust, the pressure of the exhaust gases at the nozzle exit might differ from the ambient atmospheric pressure. This pressure difference acts across the area of the nozzle exit, effectively adding to or subtracting from the total thrust. This is why engine performance changes depending on whether you are in the atmosphere or in a vacuum. To understand the motion, we look at the rocket at a specific moment in time compared to a split second later. Initially, the rocket has a specific mass and velocity. A moment later, the rocket has lost a tiny bit of mass, which became exhaust, but it has gained velocity. According to Newton's laws of mechanics, the change in momentum must equal the external impulse applied to the system. By substituting the expressions for momentum and simplifying, we are left with a fundamental relationship where the change in velocity depends on the exhaust speed and the changing mass, balanced against external forces. For a rocket launching vertically, the external forces working against us are gravity and aerodynamic drag. When we analyze the flight, we usually assume that gravity is roughly constant for a launch into low Kerbin orbit. However, the drag term is more complex. It cannot be solved with a simple calculation because drag depends on velocity and air density, both of which change constantly as the rocket climbs. In our calculations, we simply treat this as a drag loss, velocity we lose to the atmosphere. To find the total change in velocity from launch time 0 to burnout time, we isolate dv and integrate both sides. When we account for the thrust in a vacuum with no external forces, we arrive at the famous Tsiolkovsky Rocket Equation. This equation calculates the total change in velocity based on the relationship between the initial mass and the final mass. In engineering and physics literature, we often replace the raw exhaust velocity with a term called specific impulse, or ISP. This measures the efficiency of the propellant. It is defined as the impulse delivered per unit of weight of fuel consumed. Let's calculate the performance for a single-stage sounding rocket consisting of a command pod, a parachute, 4 basic fins, and a single solid rocket booster called the flea. First, we identify the system parameters. The total initial mass, or wet mass, is 2.48 tons. To get the propellant mass, we subtract the engine's dry mass from its wet mass, which tells us we have 1.05 tons of solid fuel. The engine's specific impulse is listed as 140 seconds for atmospheric operation. The rocket equation relies on the ratio between the full vehicle and the empty vehicle. By subtracting the fuel from the total, we get a final dry mass of 1.43 tons. Dividing the initial mass by this final mass gives us our mass ratio. By taking the natural logarithm of this ratio and multiplying it by gravity and the specific impulse, we get a final result of 756.2 meters per second. Since achieving low Kerbal orbit requires approximately 3,400 meters per second, this result indicates that our vessel is incapable of reaching orbit, classifying it effectively as a suborbital sounding rocket. I invite everyone who has the chance to play to try building this same rocket. Verify for yourself how our calculations match the maximum velocity reached during the launch, and prove that Kerbal Space Program is a competent simulator that truly respects real-world physical laws. If you enjoyed this video, please leave a like and share it to help the channel grow. Thanks for watching.